Hello.
Yes, Doc.
Is it that the time is not favorable for most of you, or people are no longer interested?
Doc, is the time because
The time?
Monday, yeah, Mondays look quite busy time, busy day. So it looks like most of us are on their busy schedule. That's why. But I learned some others too are having network challenges.
Oh, okay. So which day will you prefer?
Probably, unless we discuss as a group, then we alert you the day that will be okay.
Okay. I think for the time being, I'll get one day in a week be favorable for me. So, and that will also give you ample time to practice, because I know most of you are working, and if we have to do a lot in the weekend, you are not able to practice, it will not help. So we do once in a week, then I'll give you the videos, you can practice it yourself. And also, I'll also give you some exercises to do. So for those working in the course of the week, it should be, you should be able to do it. That way, I think it will be more beneficial for you than just rushing through and not, getting anything at the end.
Yeah, it's
So,
true. It's true.
yeah, once a week, 2 hours a week, I think should be okay. And actually, after just introducing you to the program, you learn by yourself, by practicing. If you just attend the lectures and you don't practice, you will not gain anything. You learn by practicing. So I think, so just decide on the day which will be favorable for you, then let me know.
All right, Doc.
But it's likely that when school reopens, I don't know my schedule for now, but when school reopens, things may change.
But Doc, which day will it be favorable for you so that we can decide on that day?
Okay, so for now, because we are still on holidays, I'm okay with every day for now. Maybe the time 3 to 5 is also okay for me. But when school reopens, as I'm saying, I don't know my schedule for the semester, the second semester. So when school reopens, it may happen that some days may not be favorable for me. But for now, if you decide on any day between 3 to 5, I think I should be available for, unless there is an emergency meeting or something that I have to attend. And in that way, I'll let you know.
Oh, okay. Okay. So we will discuss as a team on the day be okay for each and every one. Then we will let you know.
Okay. All right.
Okay.
So I've shared my screen. Can you see it?
Yes.
Okay. So the last time, getting to the end of the lecture, I rushed through. So today, I'll take my time. We'll go over the same thing, and we'll try to do it in another way for you to see the different ways you can model, let's say, a truss or one-dimensional structures or elements. Then the most important thing is how you analyze the results, how you get your results, and check whether these results are right. So, today we will go over the same thing, but we will add more details so that you know how to model anything that is one-dimensional. Then after this, I'll give you some exercise to do, maybe an exercise, for you to do. And if you're able to do it and send it to me, I'll check it, then give you feedback. Yeah, so that's what we'll be doing today. All right. So the last time, did you have any question? Is there anybody who has not still been able to install the program? So it means that everyone has been able to install it. And is there anyone who did not understand what we did the last time at all? So that maybe if I have to go over, take my time to go over. I know there are some who are yearning for more advanced stuff, and for them, these introductory lectures may not be really beneficial for them. But I'll just ask that we exercise a bit of patience so that those who are now learning the program can also come up. Yeah. So anyone who needs any.
Yeah, I think last week I had a network challenge, so I couldn't follow. But I learned this morning the video has been shared on the platform, so probably we'll look through the video then. We'll see whether we can follow.
All right. So sorry that the video delayed. Actually, the guy is in charge sent it to me. I think last Thursday, but the name that he used, I did not see it. I was expecting his actual name, but he used the e-learning center, and usually we get emails from the e-learning center. So I thought it was one of those mails, so I didn't open. It was just this morning when I called him that he said that that's the name that he used. So sorry for not sending it in time.
No problem.
Okay, I thought someone else was talking. Okay, so
hello, Doug.
Yeah.
So it means that today you'll be starting all over again, or you'll be starting at where you rushed to.
Oh, we are not starting all over. Of course, we will do the same thing using a different method. So it will be like this going over. But I'll just highlight on some few issues. Then we are going to use the same model. If you were able to follow through, I'll ask you to open yours. And then as we learn, as we go on, you can compare with yours. Unless maybe if you want to just follow mine. But if you were able to model the trust, you can open it so that you compare the results with yours to see whether everything was done right.
But Doug, we couldn't go. We couldn't get to where you got because of network, and then how you went through it.
So you couldn't get to, you
So
couldn't
we
follow
got to
through.
a place where we couldn't model it again. So I don't know. That's why I was asking whether where you rush to, you can go back to that side and then.
Okay,
Yes,
I can.
we got to a place, but where you rush through the network and then other stuff also interrupted.
Clinton,
So
are
we
you
couldn't.
talking for yourself or for the whole group?
I also
that you couldn't. Yes.
Hello.
Hello, Doc.
Yeah.
I also had the similar experience, so that's why I said probably the video that you sent. We are yet to go through the video, so maybe we can get understanding on how you rush up on the other side, the latter side. But since we've met today, I think probably you can just throw back on that so that we have more understanding on it.
Okay. All right. So I will briefly go over what we did the last time. I know there are others who are yearning for the advanced stuff, so you don't have to also waste too much time on this introductory stuff. Okay, so we wanted to model a trust. So okay, I gave you the question. You have the question, but it's showing now on the screen. Can you see it?
Yeah.
Okay. So this, you have done this finite element method with Dr. Jones. You've done the theoretical part, and you can use it to analyze different structures in different shapes and sizes. Now, we know that the finite element method, it's supposed to give us, hello, the one with the, for now, maybe you cannot mute so that if I ask a question, then you unmute for you to respond. So the most ideal solution for us will be through using an analytical method. If you have any problem that you need to solve, and the most ideal solution will be using the analytical method, where you can use known equations to do the calculations to get, for example, your reactions, your displacements or deformations, and your stresses. This will give you, accurate solution. But sometimes, depending on the nature of the problem, it becomes very difficult to use the analytical method to solve. So the finite element method is used to give an approximate solution. For very simple problems, you may get the finite element method, the solution from the finite element method, being almost the same as the analytical method. For example, this trust that we analyzed or we modeled the last time, we can get the analytical solution, get the reactions and the displacement. And because this is very simple, if you use the finite element method, the solution the reactions that you get at the nodes, at the support, should be almost the same. I think the one we did, I've compared it with the analytical solution, and they are just the same. But this is for this simple stuff. But when you have, for example, three-dimensional solid elements or members, it will be very difficult for you to use the analytical method. So we use the finite element method to get an approximate solution. So this finite element method, if you do a good work, or if you do a good job, then the solution that you are going to get should be very close to the analytical method. And because some of these structural members or structures are so complicated, you may not even know the analytical solution because you can't solve it. But then at the end of the day, there should still be some kind of accuracy. You should be able to show that the results that you are getting from the finite element method is indeed accurate, or it can be relied on. That is the word. It must be reliable. Otherwise, it becomes difficult for us to accept the solution. So, okay, we started with this simple truss, and we modeled it. And for the modeling, there are a number of stages. Hello?
I have a question.
Okay, Clinton.
Doug, so can it also be that maybe using Abaqus to model and analyze, you can compare your analysis to other software, like as you said, Answers or any other software that you also have, so that you compare the answers or results to see whether they are matching or they are not, so that you can determine whether you're on the right path. Is that also the case?
I think the issue is not about the program that you are using, whether ANSYS is giving you a better results than Abaqus. If you don't know let me just say, for example, if you don't know how to drive or you are not an experienced driver, you cannot say whether you want to compare your driving skills with a Benz and maybe a Toyota. Can you say that, oh, maybe if for Benz, I can drive well, but with Toyota, I'm not able to drive well. It all depends on you. If you are experienced enough and you know what you are doing, you don't need to compare programs. One program should be okay, but you should always be able to compare your results with a known solution, which is maybe the analytical solution, or there are ways of doing it. As we advance, you get to know. So comparing two programs, I mean, it's not necessary. Once you are using Abaqus, it should be enough. If you are using ANSYS, that should be enough. But whether we can trust your results depends really on you yourself, your level of experience. It's not about the program. So if you are using Abaqus and you are getting wrong results, it's very likely, unless you are very experienced in using ANSYS, then you can say, okay, for ANSYS, I can model very well. But once you know one, the other should be much easier. So if you learn one, it's okay. You can stick to it. And for example, Abaqus, you can use it for almost everything, unless there are some special problems that will require you to use special softwares. For example, when you are doing fatigue analysis, there is an extension of Abaqus, FE-Safe, that is used for fatigue analysis. You can use Abaqus to do very simple fatigue analysis, but for very complicated stuff, FE-Safe will give you much better results, or you can use it to do much more. The same with, for example, if you are doing earthquake, or this program, I mentioned it the last time. Okay, when I remember, I will let you know. So, the main issue is you the one doing the modeling. As we say, garbage in, garbage out. And the most important part of this is not just getting the model, getting the colored results. How you analyze or interpret the results is the most important part. And that it will also depend on your level of understanding or knowledge of maybe solid mechanics, how you understand stresses and strains, your basic mechanics, support reactions. These are things that you should know by now so that you can do good interpretation of your results. If you don't know this basic stuff, then you get the results all right, but you can't make good use of it. Okay, so in order not to waste much time, let's go over what we did. So you have the truss in front on the screen, and I think the members, there are 7 members, 1, 2, 3, 4, 5, 6, 7. So 7 members, 1, 2, 3, 4, 5, 6, 7. So these are connected by nodes. So we will have 5 nodes, 1, 2, 3, 4, 5. All right. And we are supposed to, according to the question, we are supposed to, let me get the question again. We are supposed to determine the deflection and maximum stress of the members of the truss shown below. So maybe I should have added that we should determine the support reactions, the maximum deflection, and the stresses in the members. Yeah, so you can add the support reactions, very important. So to get this, we can, for this simple stuff, we can use analytical method to solve. So to do this using Abaqus, first of all, we need to define, when we come to the, when we open Abaqus, the first thing we need to do is to define the model. So we have, if you come to the model tree, you see here. So for example, if there was nothing here, if this was just a new page, everything is new, you can double click on this one. Now I have 4 models here. Can you see these models? I have model 3, model 4, truss, and truss beam. So maybe for yours, if you've not added any model, you can see that you have only one model. If there is nothing here, if you don't have anything at all, you are going to begin all over. Then you double click on this one, and then you start with you start defining your model. So you can always give it a name. You can right click on it, on the model, right click on it, and it will ask you to okay, yeah, after you have created a model, you have to give it a name. So it will ask you to rename it, but if you don't mind, you can leave it like that. If you don't have many models, then you can just leave it model 1, model 2, if you know which one, what it's referring to. But it's always advisable to give it a name that you can use easily, that can help you to easily identify the model. So then, after you define the model, you come to for now, as a beginner, I would advise you to stick to this, follow these steps, right? Can you see?
Yes,
Hello?
Doc. Yes, Doc,
Yeah.
we
Yeah.
can see.
So when you come to the module, where we have module, and you click on the down arrow, the arrow pointing down, you will see that we have different modules. We have the part module, property, assembly, step, interaction, load, mesh, and so each of these module has something particular that you can do. So the first thing that you need to do is to define the part. So when you click on part, then the tools that you will need to define the part, that is to draw the structure or the elements that you want to analyze. These tools will be displayed, and you'll be able to do that. So for this initial part, I think if you watch the video, you'll be able to follow. So define your part, then the property. The property is where you are going to define the material properties. So if it is steel, you need to give the material parameters like the Young's modulus, the Poisson's ratio, the density. These are the material parameters. So to define that, you click on this icon that is showing like, you see, it's like a straight strain curve. Can you see that?
Yeah.
So if you click on it, it says that create material. So you click on it, then you can give it a name. For example, where you have different, if the parts, if the system has got different parts with different materials, then you have to give them names. So maybe in one model, you are going to have concrete, you are going to have steel, you are going to have different materials. Then to be able to identify which material you are dealing with, you give it a name. So give the material a name. If you like, you can give it a description. This one does not really matter whether you put it there or not. It will not affect the program. But if you want to always remind yourself, or maybe you want to send your program to somebody, your model to somebody to work on, then maybe you can give it some description for the person to be able to follow what you have done. Then when you come to the general, this is where normally for most of these parameters, for simple works, we will not specify them. So mostly you will only be using the density when you go to the general. For me, most of these materials properties, I've never used them. So the density is the key property here, you specify it. Then you come to mechanical. Here you are going to specify the mechanical properties like the elastic modulus and if you have different other. For now, the program the truss that we did, we just use linear elastic material properties. Later on, when we are doing more advanced stuff, we will need the plasticity, the plastic behavior. We have to define it. So for the elastic behavior, you only need the Young's modulus and the Poisson's ratio. So if I click on it, you see we have Young's modulus and Poisson's ratio for the elastic behavior. Later on, when you are doing advanced stuff and you need to define the plastic behavior, there are different material models for plasticity, which you have to select one that that accurately describes your material, the behavior of whatever material that you are going to model. So for concrete, for example, mostly we'll be using this concrete damage plasticity. There are other models for numerical material models for concrete, but mostly with the concrete damage plasticity is very good. And for example, we also have the concrete smeared cracking model. I think there are 3 models for concrete, which we can use. Okay, so this is for the material parameters. You will not define them again. We have done that already. Then after you define your material, you also have to create section. You have to create section. So the section is where you are going to specify the type of, for example, whether it's a beam, whether it's a solid element, that whether you are going to use solid elements, shell. It's like, how is the shape? It has to do with the shape of the system or the structural element that you are dealing with. For example, for one-dimensional structures, for example, a beam, you see, you can say it's one, though it could be 3D, but we can say it's one-dimensional because in one dimension, maybe it's much longer in the span than in the width. So we can say that it's one-dimensional. So then we will use a beam. And then when we come to the type, we can either use the truss or the beam. So the last time we modeled using the truss, today I would do the same thing using the beam, and you are supposed to get the same results. Just that if you use the beam, there are some extra parameters that you have to define. The truss is the most simple way of doing it. But for example, if you want to model reinforcement steel bars, then you can use the beam or the truss. But if you use the beam, there are some extra parameters that you have to indicate. So if your member is say a solid, then you select the appropriate material, the section type. If it is like a plate, very thin in one dimension, and maybe in other 2 dimensions wider, then you can use a shell. So depending on the nature of the structure that you are modeling, when you come here, when you are defining the section, then you have to select the appropriate section type. Okay. Then after you have created a section, then you have to assign the section. So first of all, when you are assigning the section, it would now apply the material properties that you defined to the model so that it would have those material parameters. Then assembling is how you arrange the the structure or the parts to form the actual structure. So for example, like the bicycle is an example that I use. If you model the different parts of the bicycle, the frame, the tires, the seat, whatever, the spokes, when you finish everything, you have to, because you do them individually, then you put them together to look like what it is in real life. So here you are putting the parts together to form the entire structure. This is what we mean by assembling. Here, there are some tools that you use to do this assembling. You have to change the orientation of some of the parts so that they will fit exactly into to form the actual structure. But for this one, this truss, we will not change the orientation. It is just one, so we just take it like that. But when we are doing maybe reinforced concrete beam, we will make use of these tools here to be able to position our reinforcement, our stirrups, and any other detail exactly as it's supposed to be. Okay, so that will be for assembly. So the steps is where you define the type of analysis procedure that you want to use. So here we have different types of analysis procedures. So for example, we have, for now, for static problems, maybe the load is not changing with time. It's static. So we use this static general. Mostly you use it for very simple simulations. And if the loading is not dynamic, then you use this one. But if the loading is dynamic, then we have, for example, the dynamic explicit. See, for this one, that is not displayed. So we have dynamic implicit. We also have dynamic explicit, and there are other. So for the dynamic explicit, you can also use it for static problems, but you have to define it in a particular way that will not introduce dynamic effects in your model. Because if you have dynamic effects showing, then it will affect your results. So there are ways to do it so that it will always, okay, yeah, I found it. So okay, it's still not showing. Okay, so there are ways to define it so that even though you are using the dynamic explicit, but it will appear like it's a static problem. So this is where you define the analysis type that you are going to use. This one, you can follow it from there. Then this interaction is where you have, if you have different materials or different parts that are touching, or maybe one is embedded in the other, and you need to define how they are interacting. For example, if you have steel rebars or reinforcement in concrete, so there will be some kind of interaction. You need to define this interaction. If you have, for example, a column, a steel column, resting on concrete base, then there is some interaction between the two parts, and you need to define that. So, but for this one, we are not going to use it, but later on we will use it. After that, you define your load. How is the load applied in the model? For example, in this truss, we know that the load is applied at the middle node, bottom of the truss. So you apply your load, and then boundary conditions. So the last time, I think we applied pin on both sides, but the question actually said, I think one side is pin, the other side is a roller. So we will go over again, and when we are doing when we are modeling using the beam, I will use the right port so that we see it. Then after you've done this, you have to mesh your model and define the type of elements that you are going to use. So if you are using a truss, if you are modeling this as a truss, then when you go to the mesh model, we have element types. You have to select. So when you see here, when I select the mesh model, then I come here, I click on mesh. You see that here we have element types. These element types, okay, so I have to put it on part. So element type, it says that select the model first. Okay, so I've selected. Then you see here, when you come to element types, under family, we have got different types of elements that you can apply. But you cannot use, you can't just use these elements anyhow. The type of element that you are going to use must be consistent with the nature of the problem that you are solving. For example, we model this as a truss. So when we come to the element types under family, we have to select truss. If you select beam, it may not be able to solve because you will need to then put in some extra parameters which you may not have done. So and also here, okay, because we modeled it as a one-dimensional element, we are not seeing the 3D. So there are a lot of other elements that are not showing. Now this program is giving us the elements that are maybe consistent with the model that we have created. Otherwise, you will see like if you model it as 3D, then you will see 3D elements. There are other types of elements. So for this one, we select the truss, and then every element that you select has got a name. So you see here, when you come here and over here, you see the name is displayed here. So you see that this abbreviation is saying 2D, 3D, 2T to 3D2, T to D2. So it says that it's a two-node linear 2D truss element. So every element that you select, it gives a name. See, so when I selected a pipe, can you see that the name has changed here? If you select a beam, it will be the same. So here, this one is B21, just to describe the type of element that you are dealing with. So that is for that. Then after you've assigned the element, then for this one, we create a job. So the job is like when you have done everything, you are done with everything, and you are now going to analyze. So you are submitting it for the program to process for the processing. So you double click on job, then you create a job, and then after that you submit. But before that, you can when we are doing the other one, I will take time to explain this. You can check whether you have done everything right. So you do data check. If just before you submit, just check and be sure that everything has been done right, then you can submit. Okay, so let's go over what we did the last time. I mean, just let's look at the results. Then before we do that, there is something very important that we need to look at, which we did not define. We see when we come to the model tree, can you see the model tree? We have under the model tree, we have parts, materials, sections, profiles, assembly, steps. Just after step, can you see field output request? Hello?
Yeah, doc. We are following now.
Yeah, can you see field output request?
Yeah.
Yes.
Okay, so this is very important. This is where you are going to get your results. For example, if you are interested in the displacement, this question said we should calculate or determine the support reactions, the maximum deflection, and the stresses in the members. So for you to get that, you must select the field outputs that you are interested in. So because we need the stresses, we need the displacement, we need the reactions, we have to request them. Of course, there are default field outputs that even if you don't select, they may come. But if you are interested in some other field outputs that are not part of the default field outputs, then you have to define them. So if you double click on this one, so this one, you see we have F output 1. This is, created automatically for you. So you can double click on this one and see if there are some field outputs that you are interested in, which are not selected here, or there are some that you don't need, which have already been selected. Now, the more of these field outputs that you have, the larger your analysis is going to be. The data that will be output data is going to be larger because you are requesting a lot of information. So if you have so much information, then you are going to have a very huge output data. And this is one of the things that can delay or slow down your analysis. If you are requesting so many information, it can slow down the analysis, or the output data will be very large. Sometimes when you run very large models, you can have your output, the size of your data, the output data can be in gigabytes. So you don't want to have, maybe you don't want to use so much disk space. So you need to be careful if there are output requests that field output requests that are not necessary. Don't deselect them. So when you come to the field output request, can you see? Are you following me?
Yes.
Okay, so this window that is opened, there are some information that you need to know. So you see here under frequency. Frequency is how often should the output request be written to the output file. So we have, if you select last increment, then it means that it's not going to write anything to the output file until everything has been done. So you have only one output. And that may not be really, unless you are, for example, in this program, this question that we are solving, we are only interested in the last, the result, the output. So we can just say that the last increment. But if you are, there are some programs, for example, if you are interested in the load displacement curve, you want to see how the behavior of the system as you apply the load. So you want the load displacement curve. So you need some data points. So in that case, then you have to select maybe a certain number of increments. So for example, when you say every n increment, then you define what n should be. If you say every n increment and you say 1, it is the same as like saying every increment. So, but here you can say maybe, for example, if the analysis is going to be a bit longer, you can say maybe every 2, n is going to be 2, n is going to be 10, so that you don't have to, getting the data for every step is going to be, it can be very large. So you define n to, any number that you are sure will give you the behavior that you are looking for. This one, when you start doing the advanced stuff, you understand. Then we can also define it evenly spaced intervals. So here, normally, this is what I used. For example, if I'm plotting the load displacement curve of this whole system, I need maybe 10 data points or 20 data points. So if I say every evenly spaced time intervals and I define 20, so it doesn't matter how long the analysis is going to take. It's just going to divide the time interval from beginning to the end into 20 and write the data to the output file. So I'll have maybe 20 data points, and which is enough to plot whatever curve I am interested in, so that I don't have to waste. Somebody will say maybe 100, 500. The larger this value is, it means more data is going to be written, and it's going to be larger size, and also can slow down the analysis. Okay, so that is very important. Then when you come to the output variables, we have stresses. So we are interested in the stresses. So if you click on this arrow, it will display the stress fields. So we have different stress components that you can. So for this one, the first one, stress components and invariants, I mean, it should be okay. Or the Mises stresses can also, we can include that one. If I mean, this should be okay for the stresses. Then strains also, we want the total strain components. We want the plastic strain. Because this one we are dealing with a linear elastic behavior, we don't need a plastic strain, so we can deselect it. The PEQ, equivalent plastic strains, we don't need that, we can deselect it. So if you don't need any of these and they are selected, it means you are going to have larger output values, which for nonlinear problems can delay the analysis. So you can deselect the ones that you don't need. And then this one, logarithmic strain components, mostly is necessary. So we can leave that one out. You can leave that one there. Then you come to the displacement velocities, and okay, this one, we want the displacement, the nodal displacement. For example, where we apply the load, there's it's going to, that section is going to move downwards. So we need the displacement. So this one, it's okay. If you select this one, there are different components. We have the X, Y, and Z, but this one is 2D, so we are going to have physical displacement. So this one will be able to give us that. If there are other displacement values that you need, you can select more. This is enough, so we have that. Then we also need the forces and reactions. So here, if we have this reaction forces and moments selected, that is going to give us the reactions in the horizontal and the vertical and horizontal reactions. So then when we come to contact, you see here, by default, contact has been selected. But in this problem, we don't have any contact. So we don't need to. Of course, this problem is very simple. So even I think in less than, in a few minutes, it will be solved and you get the results, even with the contacts. And of course, there is no contact, so it's not going to, give you any values for contacts. But once this problem does not have any contact, you can other output, field outputs. Now, when it comes to failure, it's going to be, this one is going to be important when we are dealing with, for example, 3D members. So we need the damage in compression, the of the material, how it is damaged. Is it compressive damage, tensile damage? We use it to, interpret the behavior the, the material. There are different, for example, this scalar stiffness SDG is also important. So important, you select them. For example, this damage initiation criteria is also important, but it depends on the work that you are doing. So all these are field variables that you can select them. Those that you don't need, for now, we don't need this failure, so you leave it out. All right, so this is for field output request. So after you have selected the frequency at which the data should be, the field output data should be written to the output file. You then select the field outputs that you are interested in. Then you say, okay, so this is created. You can give it a name that you like, but this is okay. Then we also have history output request. So you double click on the history output request. The history output request, for example, for this problem, we want to find the displacement at this node, the middle node. So we can, if you want to see how the displacement is changing with time, or as the load is applied, how is this node being displaced? We can define it so that it just keeps track of how this node is being displaced. So that after, of course, if you don't define it, you can still get it, but from the field output request. But sometimes it's better if you use the history output. It gives you the history of the displacement at this node. So let's go back to that. So under the history output request, depending on what you are interested in, if you want to say, for example, you want to see the how the reaction, the support reaction is changing, you can define it from here. You can define so many things from here. But here, this energy here is very important when you are dealing with, for example, whether there are dynamic effects in your problem, in the analysis, the results or not. But now we are not going to use it. So let's leave it like this. Later on, I will show you how to use it. So this is for the history output request. You define it, and just like the field output request. Okay, so I think now let's come to how we analyze the results that we have obtained. That is what is most important. You want to, for example, you want to write a report, you want to submit, for example, when I give you an exercise, I don't expect you to send me your Abaqus file that you created. No, I won't be able to run every one of you too. But what I need is, I need a report. You have your results, you have copied these results and sent it to either Excel or maybe Word, then you send me. So you show me where you have your reactions, your support reactions. You have the displacement at the specified node. You also have the stresses in the members. You just export this to Word and send me. I just need a Word file that is maybe your report. I don't need the Abaqus file. So you must know how to get these results and how to use the results if you are writing a report or whatever you are doing, how to get your results. So let's see how we do that. Okay. So let's go back to, we created a job. So if you want to see your results, you right click on results, and then you go to sorry, you right click on the job, the name of the job. Here I gave it job 1. So I right click on this and I go to results. So when I go to results, if the program, if the analysis was completed, it will show me the results. So here I need to analyze these results. So first of all, I will come back to okay, so this is what you will see when you come to the results. The model will be in green. So in this way, you are not seeing anything. It's just what you modeled. So if you want to see maybe the stresses, the strains, the reactions, and all that, you click on this rainbow icon. So it says that plot contours on deformed shape. So when you click on this, you will see can you all see the truss, the deformed truss?
Yes, please.
Hello.
Yes. Yeah.
Okay. So we can see some parts are red, some are in blue, some are in green. Can we all see that?
Yeah.
Yes, please.
So these colors are very important. They show us which parts of the structure is in tension, which part is in compression, which part is not experiencing any, stresses. So let's come to this legend. Can we see this legend? Okay, so
Yes.
let me go to stresses. Okay. So yeah, so when we go to this legend, there are different, let me use the principal stresses. Okay. So here, this is telling us, normally this is what you get from your analysis. So this is telling us that the stress values at this, at the various, or the stress distribution in our model. So if you look at this topmost part where we have this deep red, it's saying that the stress value is 294. Okay, for some of you, you may not be seeing this. It may be showing in, is it standard form? Let me see. So come to view and view port annotation options. So here you will see general. So you will see other stuff I have disabled. So if you go to apply, this is when you open initial, this is what you see. You have this writings here showing you the name of the model and the analysis step that you defined. So if you want to, mostly if you are writing this to an output file, or you want to export this to, let's say, Word, you don't need this. You don't need this. So you go to viewport, then viewport annotation options. So here under general, you see we have state block, title block, show state block. You can disable them and say apply, so that you don't need it, because you don't need to show this. Then we come to the legend. The legend is this box here that you see where I have my S max principal. So normally the default way is the scientific notation. So this is where you are going to have sometimes you see this, but I prefer to use this fixed so that it gives me the absolute values. So it gives me the actual values. So it depends on you. Whatever you want to use, you can use scientific, you can use engineering, but mostly for me, I prefer this one. So I go to apply. Then this box that is showing here, you can keep it, but sometimes you are showing it in your report or your thesis or uh, your paper, and you need some space. Sometimes you can, if for example, if you want to let this model come closer to the legend, you don't want this box to be, interfering with. So you can just disable it. So under legend, you see where we have show bounding box. If you deselect it and say apply, it will just leave, so that you can have your model closer to the legend. Yeah. So I have disabled that. Okay. And also this legend, you can reposition it using this X and Y, this percentage viewport in X and then Y. You can, if you change these values to wherever you want. Okay, so we go to okay. So as I was saying, now let's come to the interpretation of our results. So it's showing us this is for the maximum principal stress, where we have read these members shown in red. Okay, first of all, let me which elements and the nodes we are talking about. So when you come to this, can you see this first icon with these numbers 1, 2, 3? When you click on this, then you go to, it says that this common plot options. You go to labels. Can you see labels? So you can show element labels. The element will be, for this one, each member is an element. We didn't use so many elements. So for each member, we just use it as one element because this is very simple. But for example, if this member here, if you have different elements, maybe 10 elements, then if you say show element labels, then it will give each of these elements, these 10 elements, a number. But here we have just one element for each member, one element. So if we say show element labels, and we say apply, you see that these elements have got numbers displayed on the element 3, element 4, 4, 5, 6, 7. Then we can also show the node labels. So we click on node labels. If you want to change the color, you can do so. Hello?
Yeah.
You want to ask a question?
No.
Okay. So we can also show the node labels by selecting the node. Then we go to, okay, apply. So you see that the nodes have also been given labels. Then we can close it. So now you have this, your class well labeled. We have the node labels and we have the element labels. Let me see if I can labels. Yeah, show node symbol. Okay. So can you see that now the node symbols have been added as some kind of points? Okay. So now we have our results. Let's see how we interpret this. So what you want to do, first of all, for example, if you are analyzing a member to see whether this maximum principal stress, whether the stress, whether the element is, the structure is going to fail or not, you can compare this maximum principal stress to the, for example, the ultimate stress or ultimate strength of the material. So this is where the finite element method is very useful. First of all, for example, you want to see, before you even go and do any experiment, you want to see whether the load that you are applying to this truss is okay or not. You want to then see whether the stresses are above a certain limit or not. So now we have the maximum 94, being 294 MPa. So you ask yourself, is this value greater than the allowable stress? If it is greater than the allowable stress, then you will have to redesign you may have sizes, or if you have to reduce the load, then you reduce it. If the load is such that you cannot reduce it, then you have to increase the member sizes so that the stresses will not be larger than the allowable stress. So you use the maximum principal stress to check. So this is the maximum principal stress in tension. It is 294. The red parts are in tension. And I think we can also show the arrows. Let me see. Let me see where we can show the arrows to see where we have a tension and compression. The basic plot option render. Just a minute, I want to check something. Okay, so can you see these arrows displayed on the members?
Yes. Red arrows.
We can see that members 6 and 4 are in tension. Hello?
Yes, though.
Yes, sir.
Okay, so you can see my screen now.
Yes.
Okay, so let's say that after you have shown the nodes, the members that are in tension and in compression, you want to get this to maybe put in your report. So you don't have to use screen capture. Hello?
Yes.
Can you still hear me?
Yes.
Please.
Okay,
Yes,
so
please.
you go to file. If you want to get this, you go to file, then you go to print. If you use screen capture, for example, I have screen capture here. If I want to snip or get this, it will show the background, this background, which is not nice, unless maybe if yours is maybe if your background is plain white, then maybe it could be okay. But for me, I don't like this. So I go to file and you say print. Then here you under printer, you use file. You select file. So file, you can format, you can use PNG. It will come as a picture. it will come as a picture. So PNG, normally this is what I use, and it comes as a picture. Then you give it a file name. So let's say trust, and where you want to, the destination for this file, you indicate it. So in my case, I will just, in this file that I created for this, the output results, I'm going to just say, I'll just say results. Create a folder within this. So I select it and I go to, okay. So this is written to an output file. Let me go and see. But are you following as I'm doing it, or you are just watching?
If we are following,
Oh, okay. I did not write to this output file. Let me do it again. So file print. Okay, now I've seen why. Okay, so hello.
Hello?
So it has been written to the folder that I indicated in, but I don't want to change the screen. So I can show it. I can send it to you in your I can send it to Mr. Japan for him to send it to your group. But I don't want to change the screen, so let's keep on. But it has been already written with a white background, which is nicer than if you just do screen capture or yeah. So that's how you copy whatever you want to copy to, for example, Word. You just go through this procedure, and for example, your model, after you have modeled your part and you've assembled, if you want to get a picture of that, don't use screen capture, just go through the same procedure and to get it. So after, first of all, you want to show the model with the nodes and the element labels with your stress distribution. So this is for the stress distribution. You can also show, for example, the displacement. So the displacement, we use the U. Is for displacement. So we go to U for the displacement. Then here, this resultant is like for the total. You want, for example, we are interested in the vertical displacement. So U2, or if you want to also, you can show the U1. Okay, let's start with U1. So the U1 is for the horizontal displacement. So if we click on that one, you see this shows how the nodes are displaced. So the maximum horizontal displacement is just 1. Maybe it's 1 point something, but because I have this result, I'm just showing it to the number of decimal places is just 0. So let me, if I change that, I can, maybe we can see. So, okay, so you see this one is more accurate. So to 2 decimal places, this is giving me the exact displacement, horizontal displacement. Now, if you want to know which node is showing or is having this maximum horizontal displacement, you can also indicate it, even though it's showing here, I think node 1. So you can use this, you see where we have this rainbow color, you can, if you click on this one, it gives you this contour plot options. When you come to limit, under limit, the limit tab, you have maximum auto compute, and then we have show location. If you select this one and you go to apply, it will give you the node that is having this maximum displacement. I think the field output is not, this is for stresses. Let me see if I can. Minimum, maximum. Or is it because the arrows are already? Okay, now let me see if I use the. Okay, so okay, this is for the maximum. Can you see now? It
Yes,
shows
Doc.
that node 1, when it comes to horizontal displacement, node 1 has got the maximum horizontal displacement. So this line here is showing, says that maximum 0.71, 0.73.
73.
Node 1 has the maximum. This is how you can show where is the maximum, for example, maximum stress occurring, where is the maximum displacement occurring. So you can use that to see. So this is for the horizontal displacement. We can also look at so node 1 has the maximum horizontal displacement. We can look at the vertical displacement. And so what is this? Okay. So here, we want the absolute value. The vertical displacement, the maximum is -4. Is -4, but because I have indicated that it should give us the maximum, it's saying that 0 is, larger than -4. So it's saying that the maximum displacement is 0.0, but that's not what you're interested in. You want the absolute value. So we can go back, or if you like, you can also indicate the minimum, even though the minimum in this case would be our maximum displacement. So you see here, if I say apply, it will say that node 4. Oh, sure, sorry. I want to show it rather. So node 4 is giving us the minimum, but this is the maximum displacement that I'm interested in. Okay. So this is how you can find out which node, which element has the maximum stress, which node has the maximum displacement. So this is just that, and the stresses can also be shown. So you come here, S for stresses. You can see for this one, the element, the stresses are shown with respect to the element. Okay. Then reactions, we can see the reactions at the nodes. They are there. So the maximum reaction is about 5.7. Okay, let me see the vertical reaction. We are interested in the vertical reaction. So RF2 is about 5,000. Yeah. So it's 5 kilonewtons. And if you do the analytical calculations, that's exactly what you get. It's just exact. So that's why I said that for simple problems like this, the analytical and the numerical solutions will almost be the same. Yeah. So now we want to get this to as a report or to an output file. So what we are going to do is, first of all, you go to report. You see, we have report. Under report, we have XY, we have field output, and then we have free body cut. we are interested in the field output result. So you click on the field output result, and then you come to, you are writing this as a report. So we have these variables. First of all, normally, if you are interested in the stresses, you use integration point. I will explain this later when we are dealing with 3D elements. This one, it will be difficult to explain the integration point. So if you are interested in the stresses, so this question said we should get the stresses in the members. So to get the stresses, you select position, you select integration point. Yeah, this setup, you can give it a name, the name of the report. This is going to be written as a test file that you can use. You can use Notepad++. Do you have that?
Doc, is it the ordinary notepad that we know?
Sorry.
Is it the ordinary notepad that we use, or this one?
Yeah, I don't know whether this ordinary Notepad can open, but normally I use Notepad++.
Oh.
These Abaqus files, sometimes the format, you are going to have .rpt. It comes in a way that you can't open sorry?
Word.
Sorry?
.rpt, I think Notepad can open.
Okay. So if Notepad can open, then that's fine. So you want to write this to Notepad, this .rpt is Abaqus report. So you can give it a name, whatever name you want. I have here trust report. So I want to rewrite it again. So I'll just give it trust report 1. Then this is just to give it the name. If you want to select the location where you are going to put it, you can do so, but the default will be where you are saving the Abaqus files, where you said you want to save the files from the beginning. If you don't select any location, it will save it there. Then you come back to the variables. So first of all, we want to write the stress in the members. So I go to stress, then I want to select the maximum principal stress. So the maximum principal stress, then if I say apply, please, first of all, until you have finished everything, don't use OK. If you use OK, what I've realized is that it will write it 2 times. So just use apply. So when you select the stresses that you are interested in, there are different stress components that you can, but I want to use the maximum principal stress. So I go to apply. So, okay. I have to unselect the output, the unique node. We'll come back to this later. Okay, so
Doc, hello, Doc.
Yes.
Please, can you tell it to also insert the picture that you captured?
Tell what?
Or now you have to do it manual. The picture that you captured, can you tell it to insert it as part of this?
From here?
Yeah.
No. I don't know if anybody has done it before, but it's not possible from here.
Okay.
So the picture that the picture file
that we saved.
Yeah, that you saved. It has been saved to the the location that you selected. So that one, you just take it, you open it as a picture
then you
file
copy and paste.
and copy it to Word or wherever you want to. I think Word. You cannot insert it from here.
Okay.
So here we are just interested in and this will be written as like in the form of a table. So you cannot embed the picture in. When I finish, I'll try and show the screen so that you see the file, the way it's coming out. So I have the name already as trust report 1. Now I have to select the variables. Because I'm interested in the stresses, I go to integration point. Now you cannot mix the integration point and I mean, if you want to select the stresses, and you cannot do that together with the nodal reactions and the displacement at the same time. So when because I did it before and I wanted to do it this time, I forgot to and select that one. So make sure you have only the stresses selected. So you have your integration point. Then we are not interested in the strains, just the stresses. So stresses, and I want the maximum principal stress. So I say apply. So if you go to the message area, it will show you that, the stresses that you selected have been written to the output file with the name trust report 1. Okay, so I'm done with the stresses that I'm interested in. So I will unselect this one, and then so that I can go to the where I want the reactions and the displacement at the nodes. So I go to unique nodal. So if you are interested in stresses, you use what? Integration point. If you are interested in displacement, point displacement, reactions at a point, you use unique nodal. So you select this one. Now I'm interested in the reaction. So RF, reaction force. So I'm interested in the reaction force 1. This is for reaction in the horizontal direction and reaction in the vertical direction. I'm interested in that. This one I can mix them. I can add the displacement as well. Then I'm also interested in the horizontal displacement and the vertical displacement. Then I go to apply. So this is also written to the output file. Now, when I finish, if you click OK, it will write this again because you selected them. So rather, I'll cancel. Then I go to this output file. Where do I have that one? So if I come to output file, I can see the trust report 1. The file extension is .rpt. So I will open it. So then I come to share screen. I want to show you. Okay, share. Can you see this file now?
Yes, Doc.
Okay. So when you come to the file, we have some initial statements, but I'm interested from here, this field output reported at integration point. So this is going to give me the stresses. So we have the element label. We have element 1, element 2, up to 7. And then here, integration point, INTPT is integration point. I said I will explain this integration point when we are dealing with 3D elements. So, and then this is the maximum principal stress values. So for element 1, the maximum stress is 292 MPa, point something MPa. So these are the stress values at in the various elements. So you can see which element has the highest stress and which one has the lowest. So these ones if you go to element number 3, it has negative 1.4524 exponent negative 15. So you see this one is so small, you can assume it as 0. Can you see that?
Yeah.
So when you are
Yes,
reporting, you don't need to write this. You can make this as 0 because it's so small. This negative 0 exponent negative 15 is so small. And this one too, you can make it 0 because it's so small. So this one, for example, if you modeled this, you want to maybe analyze a roof truss, for example, and you want to see where you are going to have the maximum stresses, which member is going to be most stressed. So you model it in Abaqus like this, and you can see the stress distribution in the members. So if maybe there's a particular member that has the stress exceeding your allowable stress, then you need to do something, whether you change the size or you reduce the load, whatever you want to do to make sure that this member does not fail. So this will help you to see which of the members that needs attention. So then if you come below, it tells you the minimum stress and the maximum stress. This minimum and maximum, they are just it's just using the sign. So the negative value here is saying that is the minimum value, is the minimum stress. So that means this is compression. This member is in compression, and the maximum element, the maximum stress, this member is in tension. So if you are just looking at the absolute values, then that will be okay. So that is for the stresses. So if you have a very large truss where you have so many members, then this can help you to see at a glance which of the members has a higher stress, which one has a lower stress. All right. Then we go to the nodal displacement and reactions. So here we come to field output report at nodes. Okay. So this first table is for the displacements were not written. Oh, okay, they are written here. So this table here, we have the first column. It's giving us the node numbers, node labels, node 1, node 2, node 3, up to 5. Then the second column is giving us the horizontal reaction. So you can go to the nodes and check whether these are true. So node 1, for example, has got there is no horizontal reaction. Node 2, the same. Node 3, I cannot see okay, me, I can see it, but you cannot see that now. So node 1 is, yeah, just up there. So it doesn't have any horizontal reaction. The same with node 2. So the reactions will actually be at the support. And our support from the model, the support nodes are node 3 and node 5. So let's see. You see here we have node 3. We have got some values here for the horizontal reaction. Node 3, this is node 3, and node 5. They are almost the same values. Then when we come to the vertical reaction, we have node 3 is 5,000 newtons. Node 2 is also 5,000 newtons. So the applied load was shared equally amongst the supports. We applied a load of 10,000 newtons. So because the loading is symmetrical, the supports are, is shared equally, so 5,000 for each. And this is, it's consistent with the analytical results. And also the displacement. So the maximum displacement should occur at node 4. Let's see. So node 4, where is node 4? This is node 4. So we can see the vertical reaction is negative. Vertical displacement is negative 4.2 millimeters. And this one, you see here, this is 7 point. The horizontal displacement for node 4 is 7.2620 exponent negative 18. So this is so small, so you can actually make it 0. And the others are almost negligible. So this is for For this one, this is a very simple exercise, but at least if you understand from here, it makes life much easier. I don't know if you have any question regarding the report, how it's generated, how to analyze it. The remaining stuff it's just showing you the maximum reaction forces and where they are occurring, which nodes they are occurring, and the minimum. So that's just that. Just so that you can easily pick these values and use them. Is there any question regarding how to generate the report and how to analyze it before I show the model again?
No, Doc.
Okay, then let me share my screen again. Okay, so in general, any question regarding this trust? Because I'll give you an exercise. So I think this would be for line elements. The next time when we meet, we will deal with 3D modeling. We will model a beam, and then this is where that is much more interesting as far as solid mechanics is concerned. That's where the real work is. So, but it's good if you understand this basic stuff. All right. So, you don't have any question or contribution?
Yes, Doc.
Mr. Ajapon and Kofi Sapon. Do you have any contributions?
Doc, I think we should go and practice what we asked today so that when we meet again, questions we can ask.
Oh, okay. All right. So let me see if I've covered everything that I intended to. Yeah, I think so. Okay, so you can practice this one. I will give you another truss where you will. I actually said that we were going to go through how to model the same thing using beam instead of the truss element. Can I quickly go over that? Or we leave it here? Hello?
Maybe let's leave it here and then.
Okay. All right. So you go and practice this one. Next time when we meet, we can start with that one. How to model the same thing using it is very important. That one is very important. You can do the same thing using beam as a beam, but then there are certain parameters that you have to indicate. Otherwise, it will not work. You will see that it will tell you that you have not indicated some material parameters and you get errors. But if you are modeling it as a truss, for example, reinforcement as a truss, of course, maybe even there will be no need because when we are doing reinforced concrete, we can do that. So I think it's okay for now. All right.
Is it possible to get the link early so that we can try on our own?
Which one?
Of what over today?
I mean this the recorded video.
The recorded video for today.
Now I'm not seeing that it's being recorded from the before I went off.
It's recorded.
Sorry?
I think it's
recorded.
We are
recording. It's still being recorded.
Is it still being recorded?
Yes.
Yes, Doc.
Oh, okay, okay. Then I'll get it from the e-learning center tomorrow and send it to you.
Okay, thank you.
All right. Okay, so all the best. Bye-bye.
Thank you for your time.
All right.